the stage over to Josh.
Okay, thank you. Hello, I'm Josh. And yeah, I'll get, if I don't have time at the end for Q&A, which I will try to do, I'll get Dr. Broersma my email address, and if there's actually interest in the class, that would be great, and I'm happy to answer any questions. Okay, so a bit about me. I went to Lee for my undergrad degree, majored in journalism. There might have been an intro to linguistics class when I was here, but it was like one section, and I didn't know much about the field or about it. So I didn't do that at all here. It wasn't until I got to grad school that I got back into linguistics and did kind of a half computational, half sociolinguistics program there. Worked for a government contractor up in Northern Virginia for a little while, doing machine translation, transliteration, some authorship detection, things like that. Then moved back down here, started working at OpenTable doing restaurant reservations, which has nothing to do with any of this. And I did one of these intro lectures a couple years ago while I was working at OpenTable and felt like a complete fraud. But now I'm back. I'm working at a startup down in Chattanooga called Pylon. And we are, well, when we figure out our niche, I'll let you know. But we're working on the next wave of human-computer interaction, which looks like it's going to be, given the popularity of Echoes and Google Homes, it looks like it's going to be voice-based, which involves a whole lot of what we're going to talk about today. So without any further ado, a couple disclaimers. I never thought when I was an undergrad that a whole class period would be too little time to talk about anything, but it's going to be. There's way too much to cover. So we'll miss a lot of stuff, and I'm going to talk absurdly fast, probably. And also, that last point's important. I'm going to be doing a lot of this focused on English, because that's what I work in a lot, but there's a wide variance in computational linguistics for the state of the art for various languages, especially for languages that don't have a lot of digital text data available. English, we've gotten pretty good at. German, we're pretty good at. Mandarin is probably up there too. It kind of falls off when you get into languages used in India and Southeast Asia and things like that. And there's a lot of interesting work there too. But we're not going to talk about any of it. So this is the basic structure of what we're going to talk about today. How different fields of linguistics that you may or may not have covered in this course relate to or have been brought over into computational linguistics. A few specialties that computational linguists cover, how they have accomplished their work in the past and in the present, and then I'm going to talk about myself because that's what I know the most about. Here we go. So, starting off, these all mean the same thing. Computational linguistics, natural language processing, which you see more and more these days, the NLP acronym. Human language technology, government likes that one. Language engineering, and speech and language technology, I've seen, oh hello, is a popular one in academics now, or I'm starting to see a little more. So computational linguistics, as in the name, it's linguistics, but with computers. So one of those fields that I was talking about, phonology, so the study of sound, a phoneme being the smallest unit of speech that we have, and so brought over into the computational linguistics field that's used in technologies like speech recognition, again for the Echoes and Google Homes, and before that, phone trees, please press 1 for more options, or say, and then it doesn't understand what you say next. Turning text into speech, which is also interesting when you hear some of the pronunciations that these speakers give you. Morphology, the study of form. So English has very boring morphology, but some languages, you try to do this processing Arabic or Turkish or something like that, and it gets a lot more interesting. The basics of morphology so it's used for things like search is the most basic example, like I have here. So if you Google a word like hikers, it's going to take that back down to its root, either hike or HIK, depending on whether you're, like I mentioned up there, lemmatizing or stemming it. And it'll give you results for anything that includes that stem. So it's a way of recognizing different forms of the same root word when you're looking for search. So syntax, study of phrase structure. John gave the ball to Bob, who is doing the giving, who is doing the taking. You have to parse the dependencies and get the actual constituents of the phrases. And so that's useful for answering questions, automated question answering. So who's playing the Celtics tonight? The echo has to process that into a question, determine which role you're asking for, and what slots are already filled. So you've already given it the Celtics, you've given it the playing, so that it has to go figure out who the Celtics are, and then it has to answer the question. So there's a whole lot of computational linguistic specialties, and we're not going to talk about most of these, but we'll touch on a little bit. Especially dialogue systems, and that involves speech recognition as well. Sentiment analysis you see a lot in customer service type applications. Is this customer angry? Are they satisfied? Will they be coming back or filing a lawsuit? Let's spend just a second on the first specialty there, information extraction. And my example here is a little dated, but when you have a perfectly good example, don't throw it away, just use it a couple years later. So information extraction, one of the things it's used for is looking through a section of text and finding the entities. So an entity is a person, place, an organization, brand name, any number of things. And you can see those highlighted in this paragraph here. If you're really ambitious, you pull out the pronouns too and realize that she and I refer back to Ruth Bader Ginsburg. And that's actually taking it a step beyond information extraction, but you want to recognize those when you're doing the extraction. So, how do you do something like this? It's easy, isn't it? It's not. Before you even get to the actual extraction part of it, you have to pre-process your data. You have a blob of text that you have no idea what it is, and you have to get it into a shape that's easier to work with. So a common pipeline for that is you normalize the text, you tokenize the text, and then you do whatever you were going to do with the text. So normalization involves deciding how you're going to treat the variances in your text data. So the bane of everyone who works with text data is that they didn't create the data. They're pulling it from Wikipedia, they're pulling it from Twitter, they're pulling it from YouTube comments, and it's just all awful. So how are you going to treat variances like Mr. with a capital M, Mr. with a lowercase m, Mr. with spelled out? Those are all the same word. Do you want to collapse them to the same representation? Say a lowercase mr, so that you know that they all mean the same thing when you go to process it, or not? Do you want to keep the variance in there? What do you want to do about punctuation? Those things are three different ways of doing an opening quote. The last one is a more European way of doing it, but you still see it. And not to mention the fact that if you typed your thing in a Microsoft program, it's probably going to replace that opening quote with something that's just a little more curvy, which drives us nuts. So if you don't go through this phase and lowercase your text or collapse it to a common representation, you're going to have a bad time, especially with this next step, which is deciding what a word is in your text. If we had a little more time today, we would be doing an exercise about determining what a word is. And it's an eye-opening exercise, because you realize that you have this idea in your head of, I obviously know what a word is, but then you start asking yourself questions about a sentence like this, and really what is a word? Is John's, the possessive John's, is that one word or two words? That's a more complicated question when you get to contractions, which actually he's means he is. Do you keep that together for data consistency, or do you take it apart because you know that that's actually a pronoun and a verb? Number one, what is that? You two, what is any of this? URLs are terrible. We'll see more about that later. Doctor, again, that's the Mr. problem again. Do you keep the period, when you're separating things into words, do you keep the period with the abbreviation? And if so, what do you do with the period at the end of a sentence, and how do you tell the two of them apart, abbreviation versus end of sentence? They're both theoretically going to be followed by a capital letter. The next sentence will start with a capital letter. Broersma starts with a capital letter. So what do? And not to mention words that have a lot of different common representations, hyphenated versus one word versus two words. It's all a question of the task that you're going to do next, how you want to make your decisions on what a word is. And enjoy doing that with a language that doesn't have spaces. Mandarin looks like it has spaces for the commas and the colons and the periods, but that's just the font. There are no spaces in this text. And some two ideograph words can be contained in a 3 ideograph word, and it just all goes downhill from there. So, how do you do any of this? In the beginning, back several decades ago, I should probably have started by saying that computational linguistics kind of started as a discipline alongside artificial intelligence in somewhere around the late 50s. And one of the techniques that has been popular for many years and is still used today, but to a lesser extent, is regular expressions. Has anyone by any chance heard of a regular expression? No. Good. Is this comic legible? It doesn't matter. So, this comic is about someone saving a day with regular expressions. I'm going to skip that, and you can look at it later. I'll send you my slides if you really want to read the comic. It's only funny if you're enough of a nerd to know what a regular expression is, so prepare to be that much of a nerd. So the comic says that we're going to have to search through 200 megabytes of email to find something that looks vaguely like an address. That's the punchline, and that's how he saves the day with a regular expression. So a regular expression takes natural language and makes it more regular. It lets you write patterns to recognize different variants of text. So taking that comic as an example, the regular expression, a terrible regular expression for addresses because it doesn't handle all the variants, but handles some of them and serves as an example. So going from left to right in the expression, the /d means digit, and so you're taking from 1 to 5 digits in a string of text, and then there's a space after it, so space, and then one or more letters, spaces, or the dash. So far we have 1, 2, 3, main, and then another space, and then an abbreviation for street, drive, lane, or circle. And with the pipe in between those things means only match one of these, this or this or this or this. And then it may or may not end with a period. So you can see that this looks pretty arcane as it is. And like I started out by saying, this is a terrible way to recognize addresses, because what do you do with 150 East 33rd Street, or something where the street, drive, or lane is spelled out, or something missing that altogether, or a P.O. box. So you can see how this starts to compound complexity-wise. But regular expressions are still very powerful, and we still use them all the time, despite the way they look. So for normalizing, like I mentioned earlier, you've decided that we're going to take a contraction apostrophe LL and separate that into different words so that we can process it better later. This regular expression will take one or more characters followed by an apostrophe followed by LL and replace it with the original word in front of the apostrophe, no apostrophe, and then the word will. So, useful. However, there's an old joke in computer science that goes, so you've determined you can solve your problem with regular expressions. Congratulations, now you have 2 problems. That regular expression right there, that's all one expression, and that's to recognize our old friend URLs. It's actually a bad way to do it, but people are actively using expressions like this on the internet right now to recognize URLs and highlight them in blue or do whatever. And you can start to see how someone who works with these every day might get an ulcer. But back in, the 60s, has anyone ever heard of Eliza? Does that name ring a bell? A little bit? Okay. Eliza was a chatbot before chatbots were cool. A chatbot designed by a psychologist people would sit down and type at a keyboard, and she would just ask, "How are you feeling today?" And they would type, and she would say, "Well, why are you feeling sad?" And they would answer. And after a while, the psychologist started looking at the logs of the chats that people were having, and people were getting really personal with Eliza because it's Rogerian psychology, but she was reflecting all their things back onto them, and they were just going deeper and deeper and deeper, and it became a privacy concern. Anyway, Eliza is just a series of regular expressions. I feel X, take X, put it in the next Eliza response, say, why are you feeling X? And on like that. So it's a series of regular expressions. Anything more complex than that gets really rough really fast, but that one was very successful, especially because people weren't used to chatting with their echo and doing all the stuff that we do today. The expectations weren't there. People thought they were talking to a person, even with that level of simplicity. So another technique, a programming language that's popular for teaching introductory computational linguistics is Prolog. And Prolog has a lot of similarities to formal semantics. If you go farther in linguistics and study semantics, I never got the chance to take one of those classes, so I've had to catch up later. But Prolog is based on first order logic. And so reading from the top down there, that top rule, this is two rules actually, designed for answering the specific format of Jeopardy questions. So how do you find out whether someone wrote a work and someone is an author of a composition? So that's the name of the rule on the first line. And then everything separated by commas are things that have to be true in order for that rule to be true. So first we have to have a verb, and then we have to have an author that is the subject of that verb. And really at that point it's just a noun. That next rule says that noun is actually an author because I know this because I have a knowledge base back here that lists a whole bunch of authors for me. And then the work, Little Women, is the object of the verb, and then Little Women is a composition, is a book. And so that's how you determine an author. And then that next rule down there is how verbs work. The word that you're looking at has a part of speech that is a verb. And then the lemma, which we touched on very briefly earlier, you lemmatize that word and it works out to one of these literal verbs down here, right? Published. So you can have wrote, published. You lemmatize it down to its initial form, and that's when you have a verb. So there are systems still implemented in Prolog. Haven't heard about Watson for a few years, but IBM has just started advertising it again. So they've recast it as kind of a enterprise knowledge platform. Send us your blobs of text and we'll do stuff to it. A lot of companies are doing that these days. So that was the past, except not really the past because some people are still pursuing those lines. But we're going to talk a little bit about how things are done today. So big data, you've probably heard the phrase big data. It's everywhere. And machine learning is kind of overtaking this more literal, rule-based, linguistics-based, if you ask me, approach to computational linguistics. You still see rules used, you still see Prolog used, but there's more and more of a push to do things automatically, to train a system on a huge collection of text and then feed a small piece of text into it and get answers out. So statistical and probabilistic methods are everywhere. The frustrating thing for people like me is that they're really, really good at it. So my wife loves colors. She gets a very, very calming sensation from just the right color in the room or around. But she spent a couple years as a technical editor and was just devastated the day she learned that colors could be represented with numbers for computers, because she had to edit PowerPoint graphics and get very specific colors. And she was like, they all have numbers. And this is kind of how I feel about words now, because we're reducing all of linguistic complexity to a series of long numbers, and we'll talk about how. right now, actually, because that's what this slide says. So two of the most popular approaches to this are word2vec and glove. Are there any math fans in the class? Me neither. Okay. Someone? A little bit? Okay. Basically, the idea here is that you're going to feed a giant, and when I say giant, I mean billions of tokens, billions of words, a giant collection of text into a system, and it's going to crunch on it for a while. And on the other side of that, you're going to get each word reduced to a series of numbers called a vector. A lot of times it's a 300 item series. Some applications use less, some use about 50 or so. And basically every number in that vector encodes a tiny piece of how this word is used and what it means. And so at the end of that, you get something like the bottom row there. You can do math with words, which is just so depressing. You take the vector for king and you subtract the vector for man, but then you add the vector for woman and you get something that's shockingly close to the vector for queen. And word2vec and glove are just kind of two methods of doing the same thing. A glove tends to be a little bit more semantically focused. I like its results a little bit better, but word2vec is also very popular and useful for certain things. So how do you do that? What is this fancy algorithm that you use to get the vectors out? And this is a part where actually you should pay attention, because this is where technology is going, kind of. This technique is eating software. It's used not only for NLP, it's used for lots of other things like automatic driving. But basically, this is the second simplest form of a neural network you can have. You send things into the left side, whether that thing is a series of 5 words that you've separated out from your corpus, or it's an image, or it's a little piece of an image. You do some math on it in the hidden layer, and then that collapses into an output layer. Usually these networks have, they're a whole lot higher and they're a whole lot deeper. And the hidden layers in the middle are very hidden. So this has nothing to do with linguistics, but it's a good demonstration of how a neural network works. You take a picture of a street in front of you. This is from obviously an automatic driving course taught at Princeton, yes. So you take a picture of the road in front of you. You take tiny little pieces of that picture, the pixels in it, and the hidden layers end up with something that looks like that middle there. So it recognizes lines, it recognizes edges, it can recognize other cars in the picture, and then it turns those features in the output layer into actions. Do I turn left? Do I slow down? X and Y. And this is also useful for text, though it's a little harder to visualize. You can end up with those nodes in the middle of the network that look like this. One of them might be turned on, activated as they say, when a character is near the beginning of a line or inside quotes. Sometimes they look like this and you can visualize them like this. Often it's a black box and you really have no idea what's happening on the inside. And so that's part of the downside of a neural network. The good news is you can use the same basic technique and the same basic equations to do things as different as image recognition and text processing, not to mention other things. They are very good at what they do. They're getting state-of-the-art performance, the best performance of any system in a lot of NLP tasks. Not doing so well in others. There's definitely still room for either improvement on their part or a different approach. Other bad sides are that neural networks are, for the most part, a black box. So if you have, let's say, a government regulatory organization come to you and say, how did your automatic system make that decision? You ended up hitting a pedestrian. It's math. It's the numbers. And also, you need a whole bunch of data to train one of these. So good luck if you're trying to train it on, let's say, a language that's underrepresented on the internet. Also, these word vectors that I mentioned earlier tend to be trained on corpora like Wall Street Journal type English. Some of them are trained on more conversational type speech. But if you train a network to give you your word vectors on language that doesn't look like what you're actually processing in your system, it's not going to give you the best results. Because what's it going to do with an emoji? What's it going to do with a word that someone has put 17 A's in the middle of to indicate emphasis? So those are some of the problems. So I mentioned I work with Echoes and Google Homes. If you haven't seen this SNL sketch, look up Echo Silver. It's a good time. So if you haven't wondered how these things work, I'm sorry, you're about to learn. So when you say Alexa, or Amazon, or computer, whatever you've set your thing to recognize. Sorry, back up. Who has one of these things? Who has used one of these things? 1, 2, a minority. Awesome. Okay, good. And everyone else know what they are, basically? Okay, good, because it's on our phones too, so same basic premise. Step 1 is the wake word detection. It has to know you said Alexa. It has to know you said Amazon or computer or Hey Siri, whatever. So basically it's always recording you, but all that stuff stays on the device. And every time it detects a possible wake word, it then starts recording to send. So it has to constantly be chopping up this stream of audio and determining, did I hear the first syllable I was looking for? It's like an eager puppy. Did I hear it? Did I hear it? Did I hear it? And so guess what they're going to use to do that? Probably a neural network that they've trained on a whole bunch of recordings of people saying Alexa or people saying all these different wake words in different accents, under different noise conditions. So it's actually pretty impressive that any of this ever happens at all. So all of this, like I said, is done on the device, but that's the only interesting part of the whole process that is done on the device. Everything else gets sent to Amazon and done there, done at the end system. So a brief tangent on that. Computer science is full of terrible puns and dad jokes. Speech processing came from signal processing, which makes sense. Speech is a signal, much like light or anything else. And so you have waveforms when you're dealing with light or sound. But speech processing, instead of being spectral analysis, there's this paper that stuck that called it cepstral analysis, and it's just awful. And that same paper turned the first syllable of a whole bunch of other words backwards just for fun, and it's stuck. And I'm never going to speak of it again because I never hope I have to do any of this, because then I'll have to read these papers. They lifter instead of filter, and it's just bad. So it records your audio. You've said, Alexa, call me an Uber. It's recorded it, it sent it to Amazon. It has to turn that signal, that waveform of speech, into text. So automatic speech recognition. You never thought you'd see another regular expression again, but sometimes automated speech recognition, sometimes automatic. Sometimes it's also done with neural networks, like everything else. Amazon doesn't. They use a slightly different approach, more probabilistic than that. So in order to turn your speech into text, you have to have a model of the language that you're trying to recognize. So you have to have a computational phonology to tell you what a phoneme looks like in a waveform, and then you have to know what a valid combination of phonemes is to make a word. So tangent number 2, language modeling. Again, process a whole giant corpus collection of text, and then count the number of times different features occur to determine what's a valid word. So this example here is for optical character recognition, used to automatically scan documents, like you point your phone at a sign and what does the sign say? That's optical character recognition. And that's backed by a corpus that's been processed to say, hey, INT is a series of letters that's occurred whole bunch of times in the corpus. And this bad image over here could also be WMT, but that's not ever found in the corpus. So you're probably looking at the word winter and not the word winter. And the same thing applies for automatic speech recognition, because you have to determine what series of sounds represent a valid word. It doesn't get things right all the time. If you look at some of the things that come through a speech recognition system, it can get pretty silly. But it's much better than it used to be, and that's why one of the reasons why the Echo has been so much more successful, I think, than Siri was when it was first released way back in, was it 2010? Everyone laughed at Siri because Siri was terrible. And some people say that it still is, but it's gotten a lot better over the years. And this technology is kind of just now ready for popular consumption. So Amazon lets you, as an individual, lets you go in and make your own skills for the Echo. So you can sign up to say, if someone says, Alexa, open my Happy Fun app, it sends the speech to your thing, and then you get to process it and return a response. So Alexa, call me an Uber, goes to Uber, and Uber sends you back a response. So part of what has to happen for that is that what the user says to the device has to be turned into some sort of semantic representation of what the user wanted to do. So that can be done by Amazon, and Amazon has a system that will let you give them a whole bunch of examples and say, if a user says, turn on the lights, or I want the lights on, or why aren't my lights on, map it to this action. Or you can choose to do it yourself. You can say, just give me all the text and I'll process it. The idea of a sentence, a natural language sentence, being reducible to this sort of semantic, formal, chopped up thing called an intent goes back to somewhere in the 70s, like a lot of things in this field. Comes from the earlier concept of speech acts, which probably wouldn't cover in this course, but you might. So basically, turn the living room lights on gets turned into a turn on lights intent with a slot that is basically a variable inside that thing that says which lights you want on. That is, if you name your intents the way Amazon tells you to. I don't recommend it. I recommend a different naming scheme, but that's neither here nor there. So turn on lights is the intent, room is the slot, and slot detection, if you remember 20 minutes ago, that's another form of information extraction. So you're getting a piece of information that you're interested in out of this longer, more abstract text. And so once you've received that intent and any slots that are in it, what should you do? Where are you in the conversation with the user? This is easiest, of course, if you don't have any state at all to manage. If you're just saying, Alexa, call me an Uber, and Uber's like, all right, gotcha, done, conversation over. If your conversation lasts more than one turn like that, you have to decide, okay, last time the user said, turn on the lights in the living room, and now they said, turn them off. What does them mean? They said living room last, it's probably that. I'm going to turn those lights off, and then I'm going to give them a different response. And this gets more complex the longer your conversation is and the more things you try to do with it. So assuming you do have that long of a conversation, how do you manage it? These are a bunch of acronyms that I don't expect anyone to be interested in. So there's also prologue. And of course, there are neural systems, but I don't really recommend you use them. Is that the next slide? It's not the next slide. This is that slide. So maybe you shouldn't use neural networks for generating your responses. This is a completely neural network-driven dialogue system. That first column on the left is actually the first two columns are actual user text, I think. It's basically a chat room scenario. And then the generated response is on the very right column. And my favorite one I've pulled out big for you there, because this is the state of the art for neural network response generation. It does not make sense. And that's beautiful because that means there's room for us to work. So, back up a slide. Once you have decided where you're going to take the user, once you've decided what slots they've asked for, and what your response is going to be, what is the device actually going to say? And this is actually, in my opinion, kind of the Wild West of the actual field. Because imagine trying to get from a semantic representation like lights on living room to not just one response, like I have turned the lights on in the living room, but to get to something natural sounding where the system could choose any number of variants. Okay, they're on. All right, done. Those are very simple examples, but generating the actual response data might be the most interesting part of this, and what I hope to spend a research project at work doing, but that's a little down the road. No, so once you've generated that response to the user, you have it in a text format, and then the system has to determine how that text is going to be turned into sound. And again, surprise, neural networks. So Amazon will take your text, it will send it through their neural network, which will produce a waveform. They will store that waveform on their servers and send the device a URL, and the URL will be like, fetch me this audio, and it'll stream it the same way it does music. And this is actually, this is also a very impressive recent development, that these neural network systems can get much less robotic sounding speech. When I did this presentation the last time, I spent some time talking about Siri, and how they got the original Siri voice was they had a bunch of computational phonologists sit down and write scripts of absolute gibberish. And they had it's absolute gibberish because they have to get every phoneme in the language in every different position of the sentence to vary the prosody of the speaker. So Siri's voice changes, if a word is followed by a comma. I can get you that, but then I would have to kill you, and the pitch falls by the end of the sentence. So they had a voice actor come in and for full work days just read scripts of gibberish. And I'm sure there was some normal text in there too, but you have to get all the phonemes, so some of it's gibberish. And then those recordings were chopped up by those phonologists, and the phonemes were pieced together phoneme by phoneme to get the response. Now you can pretty much do it out of whole cloth. You can send your text to the network, and the network will go boop, 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 piece of waveform, piece of waveform, piece of waveform, done. And there's an interesting company called Lyrebird. If you want to look them up, lyrebird.ai, L-Y-R-E, bird. And they have some pretty good speech generation technology. They say they'll let you record your own voice for a minute and give you a bot back, basically, that you can put in any text and make yourself say it. They do this with Donald Trump and Barack Obama's tweets. They just feed their tweets into them, and the results are actually pretty astounding. They're pretty spot on, impressionist-wise. I haven't gotten the demo to actually work right, but it works great for Trump and Obama. So now I'm at the end because this says any questions. And I actually have time, which I thought I was going to talk less rapidly than I did, but I surprised even myself. So is anyone actually interested in any of this? Can I go back and cover any of it in a little more detail? No? Anyone want to learn how emojis work? No?
I mean, like, how they work, we mean, like...
How they're represented internally in a computer. I don't...
When we say smiley face, or when we,
When you type it on your phone.
Oh, when you type it on
So, like, how does that picture on your phone, if you have an iPhone, how does it get to an Android and it's a different picture, but it's the same semantic representation?
Yeah, how does that...
I got everyone with emoji. All right. I would go draw on the board a bit, but the camera, which I have ingraciously refused to acknowledge up until this point, is pointed in this direction. So hi from the past. It was a more innocent time, and we all wish we could go back. So text in a computer, you might have heard that computers are ones and zeros all the way down. And this is true. All a computer can do is count. It can just count really, really fast. And the ones and zeros represent electrical impulses in a tiny little piece of the computer. So a 1 is on and a 0 is off. So you have to somehow get that all the way up to text. One of the first ways of doing this was called ASCII, ASCII. And back in those days, a series of 8 ones and zeros was the best way, was the easiest unit of information for a computer to access. So 8 bits, 8 bits, 8 bits. And if you're familiar at all with binary, binary only uses zeros and ones, but it's positional. So your first 0 is 0. If that turns to a 1, it means 1. You go the next position over, that means 2. So a 1 here and a 1 here means 3. You take the 2 and you take the 1. So if you do the math, a series of 8 of those gives you that last bit on the left is 128, and if they're all set to 1, you get all the way up to 255. So you've got, and really back in the beginning they were only using 7 of those because the first one was reserved for negative numbers. But so you have 7 bits, you have 128 characters to work with, 127. And you have people who spoke mostly English designing these systems. So you've got lowercase letters, you've got capital letters, you've got punctuation, a couple symbols that are reserved for use by the computer, carriage return at the end of a line, things like that. And that's it. Why would we ever need more? It's like the quote from back in the beginning of personal computers. Why would you ever need more than 64 megs of RAM? That's crazy. So it turns out we did need more, because it turns out not everyone speaks English. And it turns out that we wanted to do things like have a whole bunch of wingdings and all this other stuff. So different encoding schemes were developed over the years. And you went from ASCII and you had different code pages. We went from 128 to 255 because we finally started using that extra 1 on the end. But then, I forget the exact year, they decided, I think it was actually back in the 90s, but they decided that this wasn't going to work. And we had this thing called the Unicode Consortium, which is a whole bunch of subject domain experts getting together and deciding once and for all how we're going to represent all these different characters in all these different languages. And so now, instead of from 0 to 255, we have 0 all the way up to, it's a really large hexadecimal number. It's like 6 Fs in a row. Hexadecimal is base 16, so multiply 16 by 16 and you have it's like more than a million characters, right around a million, I think. Anyways, so you've got English here at the very beginning, and you've got a whole bunch of characters for a whole bunch of different other languages. It turns out there's room left over. We still haven't decided how we're going to represent the multiple thousands upon thousands of characters in Mandarin that we haven't gotten into the Unicode spec yet. But at the end, there are these reserved blocks. And that's where emoji come from. That's how emoji are born. They're very high numbers at the end of the Unicode block that say, if a program sees the bits FFF00FF, I want a moon with a star on it. And that's what these characters are actually named. It's, if you ever look at, fileformat.info will give you all the Unicode characters there are. And there's some very specific emoji name. And that's where you get emoji from. Interestingly enough, that's also, if you ever see weird typographical errors in tweets, like you see someone try to type an apostrophe, but it came out as a AE ligature, like an AE and then a trademark and then a quote sign. That's because a program they were using didn't handle Unicode properly, and it interpreted it as that original ASCII. So it took the series of letters and numbers that was supposed to be an apostrophe, probably one of those fancy curly apostrophes I was griping about earlier, and turned it into the 3 characters that represents in ASCII. They split that apart into smaller numbers and gave you 3 awful characters that you didn't want, but now they're there forever. Because you can't erase anything from the internet. So, any more questions for the last 4 minutes? No one? I will talk slower next time.
Well, I do have actually a quick question.
Yes.
Well, actually 2 short questions. So first, language constantly changes and there's new words that are kind of emerging every week, it seems. How quickly are the automatic speech recognition systems able to keep up with those changes when it comes to the corpora?
Well, they can't cover what we have now. But the beauty or terror of these systems is that they're recording everything you say, and they're using it to constantly, incrementally retrain their system. And they can set it up to spot trouble spots. Like I have a very low confidence that this audio file meant this series of words, and they can go back and review that. There's a whole lot of ethical discussions around that and privacy discussions around that. And Google, when they first started transcribing voicemails several years ago, devised a really clever system that let them improve their system without any humans actually looking at the data. It's really interesting, but I don't think Amazon is that scrupulous. So they're probably listening to you. Don't talk about anything important.
Well, and then my second question was actually related to pronunciation, because you mentioned that with the ASR systems, they listen to a lot of different examples of speech and pronunciation patterns. Has that also included individuals with speech-language impairments, for example, or articulation disorders where they might not follow normal patterns that you know of?
Yeah, that's a good tag question. Not that I know of, but I can't imagine them not thinking about that and not doing it a little bit. The problem is representation, just like the problem is with any minority speech issue. You have a whole bunch of, and it's just like training the text corpora to get your word vectors. If you have a whole lot of representation from Midwestern accents, it can crowd out some of the other stuff. And so, actually, case study, we were trying to submit an app through the Amazon certification process, because just like making a mobile app, you have to go through these app stores and get approved. And we kept failing we were trying to distribute it in several different device locales, so American English, Canadian English, Indian English, and Great Britain English, I think. And we kept failing the Indian one, and our system is exactly the same. We don't treat any different text differently based on what locale it comes from. And the only thing we could figure out is that the Indian tester they were using, the system just did not understand them, did not understand the phone number they were saying. And so it got it wrong every time, and they kicked it back to us every time. So we just disabled that feature and sent it back, and it went through. So it's clearly an issue of representation. And I imagine you'll see more of a push for accessibility, because these devices are great for accessibility if you can get them to understand you, if you can get them to work. It's like literally 10 till right now. That's great questions. Beautiful, perfect, timely questions.
Well, thank you very much for your presentation.